Lesson 7.5, Work, Part 2. Work done lifting. All right, we have an example or where we have a leaky bucket that's being pulled up, and we want to find the work that we have to do, and there's three factors. One, the bucket, the water, and the rope. All of these create work, and we've got to attack each one of them, and then we're going to add them all up together. Okay, so it looks like that we're going to look at the bucket alone. Now, the bucket is down here, and the bucket's force, which is 22 newtons, does not change. So it's not varying, and it's lifted up 20 meters. So this is a straightforward work problem with constant force. So work is equal to force times distance, and force is 22 newtons times 20 meters, which is going to be 440 Newton meters, which we call joules. All right, now lifting the water alone. So the lifting the water from the bottom all the way to the top. Now here's the interesting thing. At the bottom there is 70 newtons of water, but it leaks out at a constant rate and just finishes draining as the bucket reaches the top. So what would be best is for us to create a table in which we examine what's going on. So I'll call X the position of the bucket, and that'll be the height. And then I need to figure out force. And so over here I'll call 0, and up here I'll call 20. So at position 0, we're going to have the full water, which is 70 newtons. And up here at 20, we'll have 0. At 1 meter above, we are going to have 19/20ths of 70. At 2 meters, we're going to have 18/20ths times 70. And if we're here at 10, we're going to have 10 out of 20 times 70. This suggests that the force can be written as this: 70 times 20 minus x all over 20. Put a 0 in here, and you can see we're going to get 1, and we're going to get the full force. And if I put 0 in, or 20 in here, I'm going to get 0, and I have 0. So it looks like this is a good way to represent force. So force for the water is going to vary. It'll be 70 times 1 minus x over 20. And if I continue to simplify it, it's going to be 70 minus 3.5x, and that represents the force. Now the work, I'm going to look at little works along the way. So a little bit of work from here to here, here to here, and these little intervals suggest that the work is fairly constant. So I'm going to use force 70 times, oops, I've already simplified that. So that'll be 70 minus 3.5x, and then times the distance. A little distance will be delta x here. I'm going to sum up all those little works and my integral, and the position of x is going to go from 0 to 20. This is going to be 7 minus 3.5x dx. Put it in the calculator, and we're going to get 700 joules. So this is what it's going to take to lift the water up. Now I'm running out of room, so I'm going to go to the next screen, and I'm going to work on the rope. Now here's the rope right here, and all the way down the rope has a certain force, but the force is going to vary as the rope goes higher and higher up. We're not going to have to exert as much force. So let's see what's happening with the rope. Is 0.4 newtons per meter. Again, let me set up a table that'll help me. And x will represent the position of the height, and then I have to figure out the force. So when it's 0, I have the full length of the rope, which is 20 meters, and then I'm going to times it by 0.4 newtons per meter, and that amounts to 8 newtons. So the full force of the rope is 8 newtons. At 20, position 20, then I'll have 0 newtons here. At 1 meter, I'm going to have 19/20 of 8 newtons. At 2, I'm going to have 18/20 times 8, which suggests that this formula is going to be 8 times 20 minus x all over 20, very similar to the water problem. And when I simplify that, I'm going to get 8 minus 0.4x as a representation of my force. So force is equal to 8 minus 0.4x. This is going to help me set up my little piece of work. The force is varying, which is 8 minus 0.4x, times the distance traveled in these little intervals, and summing them all up from position 0 to position 20, 8 minus 0.4x dx, and put it in the calculator, and I'm going to get 80 joules. So this is going to be 80 joules. Remember, this was 700 joules, and this was 440 joules. Adding them all together, the total work will be equal to 1,220 joules. Okay, let's look at another problem. A problem in pumping up some olive oil in a conical tank up to the top, to the brim, which is 2 feet of the top, is filled to within 2 feet of the top. So we need to put it all the way over that tank. Now it says it looks like the weight is 57 pounds per cubic foot. Cubic foot tells me I'm working with volume, so I need to really start with taking a look at the volume of a little piece of the olive oil, which is going to be a cylinder. All of this in this little cylinder is going to take the same amount of work because all of this will travel the same amount. So that looks like a cylinder, pi r squared h, and r will be an x, the x coordinate, and h will be a little width here, delta y, which tells me I need to make everything in terms of y. So I'm going to solve for x, and I'm going to put 1/2 y squared delta y, and then this is going to be 1/4 or pi force y squared delta y, and this is in feet cubed. All right, now that I know that it's feet cubed, I can set up a force. So my varying force, my force is going to be, it looks like 57 pounds per cubic foot times pi force y squared delta y feet cubed, and the feet cubes are going to cancel, and I'm going to get my force to be equal to 57 pi over 4 y squared delta y, and this is going to be in pounds. So this is my force. So I'm running out of room. Let me go ahead and continue. I've decided my force, which is varying, is equal to 57 pi force y squared delta y pounds. And now I'm going to take a look at work. So a little piece of work is going to be force times distance, 57 pi force y squared delta y, and then I want to times it by the distance. Now, how much this little piece travels varies. So here's an example where the distance varies. Let's go ahead and make a little chart here and see what's going on. So my y position, which is going to be my height, and now I want to figure out the distance traveled. When I'm here at 0, it's going to travel the whole distance, which is 10, and when it's here at 8, it's going to travel a distance of 2. So at 1, it's going to travel 9, and at 2, it's going to travel 8, and so on and so on. So that's the relationship. So it looks to me like we can say that the distance is going to be 10 minus y. And let's see if that works. If I put 0 in, it will travel 10. If I put 8 in, it'll travel 2. So now I can go ahead and put this over here as force times distance. This will be 10 minus y. So I have an example of work where the force changes and also the distance of each piece traveling changes. So I can now sum them all up. So work will be equal to the integral, and my y's go from 0 to 8, and this is going to be 57 pi force y squared 10 minus y, and then delta y. Put it into the calculator, and I will get approximately 30.561. And remember, this is work, so it's going to be foot pounds. Remember, this portion right here was pounds, and this portion right here is feet. And that's the end of the screencast.